Okay, so let me write down. So we were doing section 2.3. So the material for today, portion for today, whether or not I finish it in class, is 2.3 fully, and then part of 2.4. So we'll finish Friday this one. So by this end of this week, that is Friday 9:30 class, we should have done 2.3 and 2.4. Now that means that leaves just 2.5 out, which is called recovering a group from its representations. Okay, while that is interesting, it is not required in what follows. So I might decide to skip that and go on to chapter 3 and come back. Okay, so the material by the end of the week, whether or no matter what happens here, irrespective of with no prejudice to the lack of proceedings here, you should do that, read that from the book and or other books, and do the exercises. I will assign a few, hopefully, definitely one, maybe more. Okay, is that clear? Okay, and one of these days I might just give you a small exam for those of you who want a apart from the midterm, I might just spring a few quiz sort of things at you. Be prepared for that. Okay. Okay, so let's say a few words about 2.4 and 2.3. So the main theorems. Okay, what are the main theorems? 2.4 is about what is Jordan decomposition or Jordan-Chevalley decomposition. For this, you might want to recall that if I have a linear transformation, let's call it T, on a finite dimensional vector space V, then T can be written as a semi-simple representation plus a nilpotent representation N, such that S and N commute. And so with these conditions, there exists unique S and N acting on V such that these hold, S is semi-simple and N is nilpotent. Okay. What does semi-simple mean? It's a linear transformation on a vector space. What does it mean for something to be semi-simple? It just means diagonalizable. Okay? That there exists a basis of eigenvectors. There exists a basis of V, all of which are eigenvectors, possibly of different eigenvalues, possibly of the same eigenvalue for S. So there exists a basis of V in which the matrix of S is a diagonal matrix. Okay. And what does nilpotent mean? It means some power is 0. Okay, if you raise it to a sufficiently high power, it's 0. And in fact, if you raise it to a sufficiently high power, it's going to be 0. Then if you raise it to the dimension of the vector space, it's got to be 0. Okay, that's an easy thing to see, because to say that something is nilpotent is equivalent to saying its what do you call it, characteristic polynomial is t to the n, where n is the dimension of V. And so many of these things, if you are not familiar with, or if you some of this linear algebra stuff, you will you might want to recall that. I mean, I understand that it you may need to revise a little bit of linear algebra, but that's part of the homework. Okay. Okay. Now there is a version which is I don't know why we don't do this in linear algebra classes. It can just as well be done there. There is a version that is for, okay, if, so let T be invertible, then there exists unique S and U this time. So such that once again T is, but this time instead of additive it is multiplicative. SU is US, they commute. S is semi-simple and U is unipotent. So like nilpotent, unipotent means if you raise it to a high power, it equals 1, becomes the identity. Okay. Now there are more details here. Okay. So in either case, so it's a good exercise to try and get this from this. Right? Given this, how do you, or given this, how do you get this? Okay. That's a, so the thing to observe, well, I'll leave that as an exercise. It's done in the book, for example, but you should probably do it without looking at the book. Okay. So assume this, how do you get this? Okay. Now there are further some details that S and T can be taken to be, they can be written as polynomials in T. Not only do they commute with each other, I mean S and N commute, S commutes of course with S, so which, and T is equal to S plus N, so S commutes with T. Right? That's obvious from the because from these two it's obvious that S and N both commute with T. Okay. Moreover, S and N, although that's not part of the statement, S and N are polynomials in T. Okay. So here you can say S and N are polynomials in T, which can be taken to be without constant term. Right, that bit may be, so these polynomials are not unique. For example, if something is a polynomial, I can add to it some polynomial, the minimal polynomial of T. Right? If S is f of T, it's also f plus m of T, where m is the minimal polynomial of T. Right? That's the, for example, or a multiple of the minimal polynomial. Okay. So now the point is that you can therefore there is some leeway in the choice of that polynomial, and that leeway, using that leeway, you can make the constant term go away. That's the point. Okay. Okay, now we want to do this, but we want to look at this for an algebraic group. Okay, so what is the point? And I think this was mentioned in Van der Kalen's lecture. So, but let me recall that. Okay, now G is for us, will be for us a linear algebraic group. And one of the things that we will learn in 2.3, okay, so maybe I should talk about 2.3 before the main theorem of 2.3 before coming to 2.4. So we'll go back to 2.3 and then return to 2.4. It says an affine algebraic group. I mean, there are other interesting things here, but one of the important corollaries of the results that we will prove is finally this structure theorem, affine algebraic group if and only if linear algebraic group. Okay, now I'm abusing language here a little bit. Our definition of a linear algebraic group was what? It's an affine algebraic variety which is an algebraic group, right? So, but here I am not using that definition. That would be this one. This would mean a closed, Zariski closed subgroup of some GLN. Okay, this would be the definition on this side. So the content of 2.3 would be that give me any affine algebraic group, or what we have decided to call linear algebraic group, that is an affine algebraic variety which is also an algebraic group in the sense that it has a multiplicative structure on the points. If you look at the loci of points, it's a group, and the multiplication and the inverse map are morphisms of varieties. Okay, so that's our definition. Now with that you can always embed it. So given such a thing, you can always embed it. So G, suppose G is a affine algebraic group. I'll say affine just to emphasize the way we have defined it. So there exists n and phi algebraic group morphism such that phi goes from G to GLN. Okay, now let us understand. See, G that's an injection. Okay, now let's see what GLN is an so in this, what all do we have to understand? First of all, we have to understand that GLN is a algebraic group. It's an affine algebraic group. Okay, so here is things to understand. Why is GLN an affine algebraic group or a linear algebraic group? So it is clearly a group, right? If you think of it as n cross n, let's think of it naively as n cross n matrices with entries in this field K, and what is our assumption on K? Algebraically closed field. That's important. So we are always taking algebraically closed field. So of any characteristic whatsoever. Characteristic does not matter, but algebraic closure matters. So you take that, and then it's a group, and I have to make it an affine algebraic variety. I have to give it the structure of a affine algebraic variety. How do I do that? Well, you can sort of think of GLN sitting inside, so this naturally sits inside AN square, right? But I can think of it sitting inside AN square plus 1. And in here I can think of, so here I can think of, let me think of this AN square plus 1 elements here as n cross n matrices and times some one more variable, okay? And how do I define GLN? I take the determinant of, so let's call this A and let's call this X. And if I take dit A times X equals 1, look at the locus of solutions of this equation. This is a polynomial equation in these n square plus 1 variables. X is a variable, so maybe I'll write a capital X. This is a matrix of variables, so this is a equation in n square plus 1 variables, and of course then the loci of solutions is obviously an algebraic variety by definition. Okay. Now that can be identified with GLN. There's a map from GLN to here, and that map is a bijection. Okay, and where do I send it? I just send it to that comma determinant inverse here. So the map from GLN. So let's call this V, right? V is equal to locus of solutions of determinant A times X equal to 1, locus in AN plus 1, AN square plus 1, and then I have a map GLN. This I claim is a bijection. So A goes to dit A, sorry, A comma dit A inverse. Right? That makes it a bijection, and using that bijection I give GLN the structure of a, think of it as a variety, affine algebraic variety. Okay? So that's how GLN is an affine algebraic group. Okay? Now, so let's see. So the claim is for some n, I can find an algebraic group morphism. This we have defined what it means to be a group morphism, such that this is this is an algebraic group morphism. Now, what did we learn about algebraic group morphisms? One important fact, that the image is, although images of morphisms need not be closed, for an algebraic group morphism it is true. So the image is going to be closed. So I don't have to worry about it. So I get that from that. Once I know that it's an injection, I know that the image is going to be closed, and therefore I have identified G as a closed subgroup of some GLN. Is this clear? So the two definitions that we have will be reconciled finally. Okay, this is the concrete definition. This is the abstract definition. That's, as we have pointed out, that's very common in mathematics. You have concrete definitions and abstract definitions. And somewhere along the, once you develop the theory, somewhere, as in this case, it's probably, it lies at the surface. It's not a very deep theorem. But in some cases, it may be a deep theorem to say that indeed all the objects that we study abstractly are no more, no less than the concrete objects. Okay? So I repeat, in this case, the theorem is not very deep. It's, it's quite easy. It lies at the surface. Okay. Now, we want to define a Jordan decomposition in algebraic groups. Now, in contrast to, some of you may know something about Lie algebras, right? There too there is a Jordan decomposition. Okay. So, however, in the Lie algebra situation, that is defined only for a complex semi-simple Lie algebra. Okay, you can't define a Jordan decomposition for a general Lie algebra to the extent that I know. Okay, you need the assumption that it is you can do this. There is a beautiful theory and it works very well but it works only for complex semi-simple Lie algebras. Okay, here in contrast, there is no restriction. It's for any algebraic group, for any linear algebraic group, there is a Jordan decomposition. Okay, so that's a contrast. If you ask me, can you say why the distinction at the moment, I don't know. Okay, maybe I'll think about it. But in any case, so you don't need any assumption on the algebraic group other than it's for a linear algebraic group. There is a certain Jordan decomposition. What is it? So, what is it for GLN? Well, it is this. Right? So, given an element of GLN, it's an invertible matrix. So, I have a S and a U, semi-simple and unipotent, which commute with each other, and T is the product of S times U. So, you know what it is here. Okay? So, now, and by the first one, I can take my G, embed it in some GLN, right? And think of an element G here. Think of it as G here, right? Write this as S times U or GS times GU as it is commonly written. This is just the same thing as this, except that since we will be decomposing several G's at the same time, perhaps, you call this the semi-simple part of G, you call this the unipotent part of G. Okay? Now, are we done? So, I can just say, look here, this GS and this GU are the semi-simple and unipotent parts of my Jordan decomposition. Well, what is the problem? These may not be in G. They are a priori only in GLN. Okay, that's one problem. What's the other problem? The other problem is this is a choice of an embedding. This is by no means unique. There are several possible embeddings, right? So, so these are the two problems. Sort of you have to the problems in the sense they are not really any unsurmountable problems. Just that you have to keep do the appropriate bookkeeping and just show that indeed when I do so intuitively you should think of it like this. Intuitively, this is all there is. Okay, if you want to think of linear algebraic groups as embedded in some GLN, you just take it as a GLN, split it, and those two elements do live. Okay, so the two theorems that you have to show are indeed these two are in G. First. Secondly, now no matter, so I choose an embedding of G in some GLN, and then I get my semi-simple and unipotent parts. Now I have to prove that if you chose some other embedding and you would you have a decomposition, your decomposition and my decomposition match. Okay, these are the things. Is this clear? But it's true that this is the case, right? Finally, so the point is, no matter the proofs are such that the proofs are very careful. How to do this very efficiently. In fact, the proof goes without talking about a GLN embedding at all. Okay, but that is just these proofs have been worked over several times, and people want a very efficient proof. Okay, so you should not, you should not necessarily be thinking along the lines of the proof. That's a proof. Not that that is not beautiful. It's quite nice to read it. But first things first, intuitively, what it is just think of it as an invertible matrix, and you are doing just this. This should not be lost sight of. Okay, so it is something that you are very familiar with. Okay, one more point here, which some of you who are familiar with Lie algebras might want to keep in mind. So in the Lie algebra thing, what do? So there is a God-given representation, so to speak, namely the adjoint representation. Right? A semi-simple Lie algebra has trivial center, so the adjoint representation is faithful. So you take that and then decompose there, and then say, no matter where I go, this is sort of my what happens. So here too, there is a sort of God-given representation, and that God-given representation is the following. Okay, so I have already started talking about representations as if, so we have not formally defined the word representation, right? So a representation, but we have defined what it means to be a G variety, correct? So what is a representation? Vector space, which you can think of an affine space, and as an affine space if it's a G variety, and the action of G is linear. That would be a representation. Is that clear? Okay. So now you think of this. This is the ring of functions, ring of certain kinds of functions, namely polynomial functions on G. Right? These are as if you want to think of this as sets. As in set theoretic terms, each element here is a function from points of G, which at G you think of as points in some affine space, and K, which is equal to K bar. So there are maps, all maps, but I am only thinking of polynomial maps now. Okay, and so it is precisely that set, right? Okay, now this could be, as you well know, this is just the, if X is G is a affine variety, G being an affine variety, Kg is just the affine algebra corresponding to that. What we wrote as Kx, since in our X is G, we write Kg, right? That is going to be an infinite dimensional vector space in general. Okay, except in trivial cases, it's going to be an infinite dimensional vector space. So there is a bit of some niceties to be observed here, because being infinite dimensional, when I talk about representations, how did we define a representation? It's a affine variety, affine space. It's a vector space which, when you think of it as an affine space, is a G variety. That's how we have defined it. Now, so necessarily it is a finite dimensional space. All our representations will be finite dimensional. So how do I make this into a representation? Well, what we will show, and that's one of the main theorems, is that this is, so give me some finite, so if you give me finitely many elements in this space, Kg, you can find a finite dimensional space, bigger space perhaps, which contains all these elements, which is a finite dimensional subspace of Kg as a vector space, and which is G stable. Okay, so the word to be used is locally finite. That means, while it is not itself a finite dimensional representation, you can pretty much treat it as one, because given any finitely many elements, you will find a finite dimensional vector space contained in this space on which is G stable. So it is a union of finite dimensional spaces. So you can essentially, for all practical purposes, treat it, it's sort of pseudo infinite dimensional. Okay, so it's okay. So this will play the role. This is the God-given. So if you are wanting to look at Lie algebras, something about Lie algebras, and want to use knowledge of that theory to solve problems here, then the thing to look at is the representation K on Kg. Of course, there is a right action and there is a left action. You can and there is a conjugation action. Conjugation action is not good because that's not faithful, but there is a left action and there is a right action, and you can use either one. Okay, and the two commute. Okay, so we will say more about this. So, is this clear? So, these are the okay. So now let's do it more formally. So we are doing 2.3. So G variety we have defined, right? I am not going to write this down. This is a variety X on which there is an action of G as a group. It's like, so variety is also a set. So on the underlying set, there is the action of the underlying group of G. So there is a map G cross X to X, right? And then that map is actually the underlying set map of a morphism of varieties G cross X to X. That's what it means for it to be a G variety. Okay? Okay. Now, so in particular, when you have a G variety X, you have a group, you have a set, and you have a G set. That is, X will also become a G set, right? And all the terms that we are used to in group actions on sets will be used, right? Will make sense, and we will use them without further comment, right? Orbit, invariant subset, right? You might even say invariant subvariety. If something is a subvariety whose underlying space is invariant for the action of the group G, you call it an invariant isotropy group, transitive action. Okay, all these will make sense, and we will use this without further comment. Okay. 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 Now, this being very special. So, in particular, if a group acts on a set, it acts on functions on that set, right? So if G, so this is just a set theory now. If G is a group, if a group G acts on a set X, then G acts on functions on X. Say normally you take real valued functions or complex valued functions, right? So how does this, so I am not specifying where the values of the functions are, it is sort of understood. So if f is a function, gf is will be another function. I have to define what it does to X. This is defined by f of G inverse X. This is the standard way to do this. Okay. Now in this situation, again, you have X is, so G acts on, okay. So what is an example of a G variety? G acts on itself G being a group, it acts on itself by multiplication on the left. So that's called lambda, lambda for L for left. Okay. On the right, that's called rho. Rho for right, R and R for right. Okay, and by conjugation. Now those, if you have a fine algebraic or an algebraic group, these actions will become, so you can, G will become a variety over itself with those actions. Okay, no problem there. I mean, there is a little bit to check. You have to make sure that the maps that G cross X to X that you get is really a map of varieties, but we know that the multiplication map is a map of varieties, so there is no problem at all. Okay, and for the conjugation you might have to compose a few of them. Okay, but okay, so now look at this and combine this with this. If G acts on X, it acts on functions. So here G is acting on the left, on the right, and by conjugation. So there is a corresponding action of G as a group on functions on G. Okay, let me take them to be k-valued functions. Okay, so so G acts. So there are corresponding actions of G on functions on G. So let me take those functions to be k-valued. Right. So for example, so lambda, okay, so one more point here. Now these so kg is a subset of functions of k-valued functions on G, right? Namely, these are the polynomial functions, right? Now you can observe that the action of G preserves this set of polynomial functions. Okay, that's an easy exercise. I won't do this, but it's also sort of intuitively clear why it should be. We are doing everything in this category, so it stands to reason that G, the action of G on all functions, preserves the polynomial functions. So G acts on Kg. That's okay. So Kg is preserved, is G invariant for all of these actions, whether it's right, left, or the conjugation. Okay, so more generally, if X is a G variety, then G acts on functions on X. The abstract group G acts on abstract functions on X. Let's say k-valued functions. Yes, it does act. Now, the polynomial functions on X are preserved by the action of G. That comes because G cross X to X is a variety map. Okay, so polynomial functions are preserved. Okay, therefore you will get an action of G on Kx. Is this clear? Okay, so another way of thinking about it is the following. Since I have this map G cross X to X, right, I can take so these are, let me take these to be G to be now an affine algebraic group and X to be an affine variety. So G, our linear algebraic group, and X is an affine variety. Then this is equivalent to a polynomial, I mean a K-algebra morphism well, what I'm saying is right, but what I wanted to somehow get from this was the G action of G action on K of X. Well, I mean, this doesn't seem to give that. In any case, it's what I said earlier is clear enough, right? Okay, this is fine. This is correct. There is nothing wrong with what I wrote, but I seem to have lost my thread a little bit, but never mind. This is all right. Okay, so there are indeed actions of G on this Kg. Okay. Now let's also define a variety. So let's also make the formal definition of a representation. Yes.
Here you said that Kg will be G invariant. But suppose I look at G cross X 2x.
Yes.
So in that case, will Kx be invariant?
Yes, it will be invariant.
So in general,
In general, it's true. Yes, yeah, it is true. That is because, see, yeah, it's a good exercise to try. Yeah. So in general, it is true that there is an action of G on Kx, on the abstract group G on polynomial functions. Okay, so to repeat, the abstract group G acts on all functions and it leaves the polynomial functions invariant. And the reason for that is because this is a variety map. Okay, so if I take, for example, little g, fix a little g and x to x, that's a variety map. So when I pull back using that gives me an algebra. No, polynomial functions go to polynomial functions. That's essentially the proof. But it's good for you to sit down and write it out. Okay. Okay. So this is the definition of what is called a rational representation of G. Okay, this word rational, maybe, I don't know if it bothers you. It is what you would just call a representation. Okay, the word rational is I mean, you can ask, why isn't it should be called polynomial representation? Why is it called rational representation? Well, that's a historical accident. Okay, so what is a rational representation? It's that something is a variety, but that variety is a vector space, which as an affine space is there is a natural structure of an affine variety on a vector space, K vector space, and with that as variety structure there is a G cross, it is a G variety, and furthermore the G action is linear. This is okay. This is what it means for something to be representation. That's very natural, except the word rational is is classically, because if you think of GLN, 1 over determinant inverse, for example, determinant inverse or 1 over determinant is a valid, what you would call, function on GLN. Okay, but it's a rational function. It's not a polynomial function. Okay, so although you might say, okay, so so although we loosely say polynomial maps, right, and you can ask, isn't 1 over determinant a polynomial map? In a sense it is, I mean, the way we loosely speak, because it is what you might want to call a regular map. It is within the category, right? GLN to K, A going to determinant A inverse, is a valid map of varieties. Okay, no problem. Okay, but it is not a polynomial map, correct? There is a 1 over determinant. It's a rational function, right? So that somehow that has survived in the terminology, and you call it for some reason rational representation. Okay, and to make matters worse, there is something called a polynomial representation for GLN, which means that there is no determinant inverse. In fact, what you have are actually polynomials without a determinant, in the sense that those maps are actually are maps on n cross n matrices restricted to GLN, so without the determinant inverse. Okay, so this terminology is a little, admittedly, a little strange, but such is this life. Okay, so rational representation of G in V. So V is a finite dimensional vector space over K equals K bar. So that's our standard notation. Okay, so he defines it is a homomorphism of algebraic groups. Okay, G to GLB. So we might use the term G module, he says, and V may be viewed as an affine variety with a G action. Okay, so the definition that is given is not he gives this definition, which is also fair enough. Okay, so if you have for finite groups, for example, you give maybe 2 definitions and say the 2 are the same, right? What's a representation? It's a map of G into group homomorphism from G to GLV. It's taking that approach where that map is now a map of affine algebraic varieties, or just algebraic varieties, because G maybe is not assumed to be affine here. So for any algebraic group, you can think of this as a representation, V as a representation of G. If this map is a map of varieties, also a map of groups, homomorphism of groups. Okay, so it says an orbit Gx is open in its closure. Closed orbits exist. So this is with the notation that X is a G variety. So G, the assumption on G is that it is an algebraic group, not affine. Okay, not assumed affine. Note, for this lemma, G is just an algebraic group. Okay. So let's prove this, or rather indicate the proof. So what does it mean to? So I'll write the proof informally here. Okay. What is it? What is an orbit? It is just take an X and see where all it is taken by elements of G, right? So once I fix that X, it's as if I get a map from G to X by G going to Gx, right? That's the image is the, so Gx equal to image of the above map. Right? What do I know about? So this is that map is a morphism of varieties. Right? And what do I know about morphisms of varieties? That is this famous 1.9.5, right? That it contains a open subset of its closure. Okay. So you have an open subset of its closure, but note that the orbit is homogeneous for the action of G. So if I have an open subset here containing some element X, I can move that to another point by just translate that, right? If I have on this orbit, this is my orbit. If I have some Gx here and there is an open set, okay, so it contains a non-trivial, non-empty open subset of its closure, right? So I take this open set, this is my orbit. The open set is, say, this one, right? But I claim this open, every element is contained in an open set. Why? Because if I have something here, which is Hx, X is, say, somewhere here, then I can take, it's called this U, I can take H inverse of U, or G inverse of H inverse of U. What will that do? Or maybe H of G inverse of U? Okay, H of G inverse of U. Okay, H of G inverse of U. That will take it to something around H of X. Okay, so every element is contained in an open subset of its closure, so the whole thing is open. Okay, so again, it is the same idea. It's a you take a statement from algebraic geometry and then use just use the group to translate the thing, and lo and behold, you have a theorem. Okay, so the same idea here. This is okay. And what is the proof that closed orbits exist? So here is, so the point is, if I have a group, an algebraic group acting on a variety, now there exists a closed orbit. That's the claim. Okay. So what's the proof? So look at, so take a variety Gx, right? I mean, there are many ways you can phrase this. See, let us look. I'll probably just say the idea behind the proof. In terms of a proof, it is not the most efficient. If you want to write a very beautiful one-line proof, you probably can, right? So don't look for the efficiency of the proof rather than the idea of the proof, okay, in what I'm saying. So let us take closure. That's also a G variety. It's a G invariant subspace, and G invariant subspaces are unions of orbits, correct? This is just arbitrary, you know, if you have a set on which G is acting, a G invariant subspace, subset is a union of orbits. That's just abstract set theory. So you can write, but among them there is Gx, which is open in its closure from the first one, and there is the rest. Okay, so Gx union rest. Now you can, so these are also orbits, right? These closures are contained in here. So this is also a G invariant subspace, right? This is a union of orbits, because this is a union of orbits, this is one of the orbits, and the rest is a union of orbits. Okay, so you take that, okay, take a closure there. That is contained in here, correct? Okay. Now, now X is an Eutherian space. I can take a minimal one among G invariant closed sets. So the idea is X is an Eutherian space, which means there is a minimal condition on closed sets, on any family of closed sets, right? I take G invariant closed sets, and there is a minimal one. Okay, that minimum one has to be closed. Why? Because if not, then you can break it up like this, and if there is something non-trivial here, its closure is contained here, and it will be G invariant, and it will be less than this, strictly less than this. All right? So
Why is that closure? That closure might still be equal to this.
no, because this has an open set which does not intersect this. Okay, so the fact that this is open in its closure implies that these closures, good point, it's a good question, yes. Right, so he's asking, suppose I take some closure here, I have to say why this closure is not equal to, this is strictly smaller. I have to say why, because look here, this is open in its closure. So this is an open set that does not intersect any of this. So no point here is in the closure of things here. This is closed because it is closed, complement and open. Okay, so its closure will be contained there. Okay, so the idea, I mean, that's the, okay, so what's the proof? So let's just write it. Again, this is not very efficient. You can probably write down an efficient proof. X being a Noetherian space. So this is part, although again we have not defined variety yet, it will be part of the definition that it will be a Noetherian topological space. Okay, that's part of the definition. So there exist minimal G invariant closed sets. Okay, so say y. So V is a G right? So if take y in y and consider GY closure. There exists minimal non-empty. All right, we can do that because for on any system family of closed sets there is a minimal condition. Okay. Consider G. Now this must be equal to y, right? Because this is G invariant and closed. So it must be equal to y. Okay, but we can, so by choice of y, we have y equal to gy bar. Okay, look at now gy bar is equal to gy union orbits. So if x belongs here, or maybe I choose a different letter, z, then gz bar is contained in gy bar complement gx, gy, for the reason that gy is open in its closure. So because gy is open in its closure, and so yes, the complement is closed, G invariant. Yes, I'm just writing out something that is obvious. Yeah, I agree. It's obvious. It's not, the main thing is to observe this and choose a minimal one. That's all there is. Okay. Okay. Now, so then, so gz bar is properly contained in gy bar is equal to y, a contradiction. Implies gy bar must be equal to gy, which means the contradiction arose because I assumed that there was something in this, in this set of orbits. This is, we've assumed this, so that is what led to the contradiction. Therefore this cannot be, which means this is empty, and therefore this is equal, which means this gy is minimal orbit, closed orbit. Is this clear? Okay. Now typically our G will be connected. Okay, in many of the cases you can sort of think of, even if your G is not connected, you can sort of look at the connected component and then work from there. And many of the groups that we will be directly working with will be connected. So these orbits are irreducible, right? And so what will happen is, so you can think like this. So here, this will be this is an irreducible closed set. This will be proper. So if you take an orbit closure here, that will be of smaller dimension than this one. You understand? So I repeat. So suppose G is connected. So here is another proof. For simplicity, let's assume G is connected. You can also make this proof work when G is not connected, but never mind. Let's assume G is connected. So, or what is the same? Irreducible, right? Remember that for algebraic groups, it's traditional to call connected, use the word connected rather than irreducible. Otherwise, it's actually irreducible. That's what it means. Okay. So Gx being the image of an irreducible topological space, the orbit is irreducible. Closures of irreducibles are irreducible, therefore the orbit closure is irreducible, right? Okay. So this is an irreducible closed set. Okay. And look at something here. Okay. This is an open set in there. This is the complement of that set. And I take an element there, take an orbit closure there. That's also, by the same logic, an irreducible closed set. If you have one proper irreducible, one irreducible closed sets contained in another, they cannot have the same dimension. So that dimension goes down. So you can also argue sort of by dimension that if you have an orbit closure contained in another, then the dimension falls. So then if this is, and from the definition of a variety, we will see that we will have the one we start with has finite dimension. Okay, so you start with a finite dimension, and so take an orbit closure. It will be contained in the variety X, and it's an irreducible closed set. Therefore, it will have dimension bounded by the dimension of X. And then each step, if it is not closed, then you take a smaller thing, and then it will have smaller dimension, and so on and so on and so on, until you can't go down any further, and that there, lo and behold, you have your closed orbit. Okay, that's another way of thinking about it. Okay, this is a very simple lemma, but it's a very important one. I think sometimes it's called even Borel's closed orbit lemma. Okay. Okay, now let us come to the, now this is important, but the next one is also equally important. Okay, let me, before even proving the lemma, which will help us prove that G will embed in GLM. This is the lemma which will help us prove that. Let me show, assign an exercise explicitly. All exercises in the book are assigned implicitly, okay? But if it is especially important, I will assign them also explicitly. But it goes without saying that if you have some difficulty, by all means ask, and I am obliged to give you an answer. Okay, so that I take on that if you ask, I have to give you an answer, right? So but you have to ask. Okay. So here, so this is exercise 2.3.9.2. It's a nice result. We can appreciate the result, and the idea is that the proof of this follows the proof of the lemma. Okay, so if you try to prove this, you will revise the proof of the lemma as well. Okay, so let X be X an affine variety, which is a G variety. So affine G variety. So G is a linear algebraic group. Then there exists an isomorphism of phi of X onto a closed G invariant okay, that will be obvious, onto a closed subvariety of some an. Okay, right now that doesn't seem very special because X is an affine variety. So it is a closed subset of some AN, right? What is special about this AN is that you can make this into a representation of G. Okay. And a rational representation. R, he calls it G to GLN. This N is the same as this N, such that phi is G equivariant. This is called linearization of actions. I hope intuitively you get you can appreciate the statement. Never mind the proof. The statement itself is should be interesting enough. Okay, so what you're saying is, okay, let's think of it for finite groups. So if you have a set X on which this group is acting, then what you're saying is that you can get a variety, a representation and a G action on that representation, right, such that this X embeds. So you have G, so what it's saying is G acting on X, right? Now you can actually, I can make this X sit inside a certain V. G acts on V, but this action is also linear. So every variety, affine variety on which G acts, I can think of as sitting inside as a G invariant closed subset of a representation of G. That's what it says. Okay. For finite groups, this is trivial because you can take V to be just the span of X. I mean, just the formal free vector space span of X. Okay. Here, it being a variety, the problem is you have to do it inside. You have to do some algebraic geometry. In other words, you have to make sure that what you're within the category of varieties. Yeah. So is the statement, I hope you can appreciate the statement even without, even before we prove the lemma. Okay. Now, so the next lemma, this important one which will help us prove that that every affine algebraic group is a linear algebraic group, says the following. If G acts on a variety X, then we have seen that G acts on its ring of functions. That ring of functions, that action is locally finite. That is, given some functions, polynomial functions, I can always find, given a finite set of polynomial functions, I can always find a finite dimensional vector space of functions, which is of polynomial functions, which is G invariant, and which contains all these functions. Okay, this is what it says. So we are doing 2.3.6 proposition. So G is a linear algebraic group. X is a affine G variety. Let V be a finite dimensional subspace of Kx. Subspace meaning linear subspace. So this is the ring of polynomial functions of this variety. 1. There exists a finite dimensional subspace W of Kx such that W contains V and W is G invariant. Okay. For the action of G on Kx, which is the induced action. Okay. So this is understood that G of F acting on X is F of G inverse X. That's the action. Okay, with respect to that action. 2. Okay. So you have some V, right? And we are saying that you can find a W such that this is true. Now we want to give a criterion for when, say, V itself is to say V is stable. Or in the, by change of notation, we'll think of W as V again, and think of what is the condition for V to be stable, right? Okay, so here is the thing. So the important thing here is, so remember that there is a G cross X to X, right, which is Kx, which is equivalent to this map. Right, and then so if I take an element V here or some F here, so V, I write V because I'm thinking of V as I have vector space V here and an element V of that V, right? Okay. Now I can look at the where it goes under that co-map, right? Co-action map. This is the action map, this is the co-action map, right? So I should be able to write, the claim is V is stable if and only if I can write this like so. V prime and some F prime, V prime in V. Or, okay, let's put this way. Let me not even write it like this. The image of V goes into V tensor Kg. Right? V is stable if and only if V goes to V tensor Kg. That's what it is. Okay. So V is stable, G invariant or G stable if and only if, okay, let's call this A, let's call this A star. So A star of V, he says, is contained in Kg tensor V. Okay, if so, meaning if indeed V is G stable, right? Okay. So what do we want to say? We want to say that this is C. To do Jordan decomposition, I said just like in the Lie algebra case, where you use the adjoint representation, here you want to do the God-given representation. The God-given representation will be on K of G itself, right? But K of G being a infinite dimensional space, you will want it to, you want to say that look here, it is a union of finite dimensional spaces. And the first one assures you that indeed it is a union of finite dimensional G invariant subspaces, but I want more. I want to say that each one of those is a rational representation of G. Okay, so that is, if so, then G cross V to V, which is obtained by the restriction here, right, is a rational representation of G. Okay, 3, I will say, just say rationality statement. Okay, that will be part where if all the data given are defined over a subfield F, then you can, the conclusion can also be done over F. That's the, okay, so far we are, so at some point I will define what it means. We'll do the basic definitions, and then it will be, left for you, to sort of go back and check wherever there is a rationality statement that such a thing holds. Most of the time it is routine, but there are places where you have to be careful. Okay, actually rationality questions are very delicate, they're very delicate, but for many of the elementary things that we are dealing with, there is no complication. Okay, so this is the statement. Okay, let's prove this. So he says, okay, let's do 1. So 1. May assume V is equal to Kf. He's doing it when V is one-dimensional. If you do it for V one-dimensional, if V is not one-dimensional, it is generated by 15 things. You just do it for each one of those 15, and for each one you will get 15 W's. You take the sum of those. That's still finite dimensional and G invariant. Okay. Okay. Now, so you look at this A star F. Taking a hint from the second part, you look at this. I want to show that it is stable, something is stable. So what do I have to do? I have to write out sort of A star F, where think of A star F, A star is this map. F, look at the image and write out what it is. So you write this out, I is equal to 1 to n, ui tensor fi, ui in kg, fi in kx. Okay. Then okay, let's look at GF. Okay, my notation slightly differs from the book. Okay, the book is a little more formal. I want to do it a little more informally. So this, by this I mean just GF. And so I'm putting it on top just to just for that it seems better, right? What is GF? So let's work this out. Okay, so GF of x is f of G inverse of x, right? Okay, but what does this mean? This is just the pullback under under this action map, right? So if I have, so I claim this is nothing but ui G inverse fi of x. So if, what does it mean here? A star is the pullback under A, right? That's what we are using here. So I take G inverse comma x here, and that goes to G inverse x, right? F, when I put, if I get a, so how is a tensor thing a function on this? You evaluate this on this and you evaluate this on this and then multiply, right? That's how it, okay. So now x was generic, so you can remove the x and write gf is equal to I is equal to 1 to n ui G inverse, these are some constants, fi. Right? So the point is, now this holds for, so this is for all G. So what have we done? I mean, it's a little subtle, the proof. So you look F, I have found this space F1, F2, Fn, finite dimensional space. I am not claiming that that is G invariant. I am not doing that. All I have said so far is that every translate of F belongs in that finite dimensional space. Now I take the linear span of all the translates. That belongs still in that finite dimensional subspace. That is G invariant. Okay? Implies, now you take this, you know, K GF, I mean K span of all GF, GF for all G in G is contained in this KF1 and this is G invariant. This is G invariant. So the point is, I'm not claiming that this finite dimensional space is G invariant. I didn't say that. The point is, all translates of F are contained in this finite dimensional space, and the span of the all translates is sort of by definition G invariant. Why? Because any element here is of the form a finite sum of translates. And if I, so if it is G1F into some constant plus G2F into some constant dot dot dot, if I hit it with a G, all those GIs become GGI, etc. And but those are all still within this space because all the translates for all G in G is contained in here. Okay? So it's a, okay. Okay, maybe we'll, I mean, we have run out of time and we'll stop here, but I will probably skip the rest of this proof and ask you to read it and also do the exercises, the particular exercise that I assign, in particular. Okay, so I'm afraid the course will be will take this sort of route where, I mean, I hope I'll have something to say that is useful, and you will find it that is useful for you to read the book. But very often it might just, at the basic level, it might just be giving you a timetable on how to read the book. Okay, so I just assign on this day you read this part, on this day you read this part, right? I hope it will be better than that, but but you know what I'm talking about. Okay, so see you on Friday morning.